As I mentioned in the last video, we can use percent compositions to find empirical formulas for compounds, but that's not always enough information to know whether that's the actual formula for that compound. To give an example of where this may be true, let's look at this molecule benzene here, C6H6. If we went through the process of finding the empirical formula for this compound, what we would end up with is actually C1H1. And the reason for that is with an empirical formula, you'll always find the lowest possible ratio. What I mean by that is if we divided each of these numbers by 6, we'll get C1H1. And so if we do an analysis where we find the mass percent and then find the empirical formula for benzene, how do we know that it is C6H6? Well, the simplest way to do this, simple is the right word, but what chemists do is we have ways of figuring out what the molar mass of the compound is. And the primary instrument that's used to do this is what's known as mass spectrometry. We won't go into the details of how this works. This is a pretty cool technique. If you continue in chemistry, you'll learn a lot more about it because it's a very powerful and useful and commonly used technique in chemical analysis. But the thing we need to know is that in a mass spectrometer, we have high-speed electrons that are shot at a sample of the molecule, and that will knock off an electron from the molecule. So we have our original electron here, and then one of the electrons from the molecule is knocked off of the molecule. What we're left with is this molecular ion that has a positive charge. The reason the positive charge matters is that we have ways using magnets or other ways, primarily magnets and electric fields, to be able to separate ions based on how heavy they are. And so that's what a mass spectrum is where we take a sample, knock an electron off of it, and then measure how much it weighs. And in the process, sometimes the molecule will actually break up a little bit more. With a mass spectrum, we get data that looks something like this in this chart down here. We get numbers of molecules here, a relative intensity on the y-axis, and the x-axis is what we call the mass-to-charge ratio, or basically it's just how heavy are the ions that we're measuring. And generally, in a mass spectrum, we'll have one peak that's at the highest end, and that's our molecule that didn't break up at all, and that tells us what the molar mass of the compound is. So for this example, for benzene, this is the mass spectrum of benzene. We know, since we get a peak here at 78, that benzene has approximately a molar mass. We don't have all the decimal places on this, but it has a molar mass of 78 grams per mole. In the next video, we'll look at how we can use that information to go from an empirical formula to get the actual chemical formula for a compound. But this is how we get that information in the first place. Now, the other thing you have been wondering is how do we get these percent compositions in the first place? And one of the common ways to do this is on the right-hand side, this idea of combustion analysis. Combustion analysis is often used for hydrocarbons in particular, things with carbon and hydrogen in them. And we have our sample, we send in a stream of oxygen, and we then burn it inside of a furnace. We know a combustion reaction leads to the formation of carbon dioxide and water. So that's the basic idea of a combustion reaction. And so we have a way of keeping track of how much water is produced. We have a compound that absorbs water, and we measure how much heavier that gets after we do this process. And we measure how much carbon dioxide is absorbed by another compound and how much the mass increases there. And so we're able to sort of separate out the hydrogen and the carbon. Hydrocarbons also often have oxygen, and so any mass that's not accounted for you would assume is oxygen. Now, this is really useful for carbon and hydrogen and anything else that combusts to a specific thing. Sulfur combusts to sulfur dioxide, you can capture that as well. But other elements are not represented. So this doesn't work for absolutely everything, but a lot of the molecules we care about are composed mostly of carbon and hydrogen and oxygen, and so this works for a large number of molecules. And so this is a way that we can get these percent compositions in the first place. So we do this by measuring what's our mass of H2O, what's our mass of CO2, and what's the mass that we started with. And then we need to go from there, from mass of H2O, we need to convert that into, gotta go back to the pen, convert that into a mass of just hydrogen. From CO2, we need to go to a mass of just carbon. And then we can compare that to the mass of the starting material to get a percent carbon and percent hydrogen. So in the next video, I'll do one example of going through a combustion analysis, finding, and with the information also of knowing what the molar mass of the compound is, getting to an actual chemical formula from an empirical formula. So we'll see you in the next video for that.